Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Guru Jambheshwar University of Science and Technology, Hisar in Haryana. Today we will be discussing about spectra of alkali metals under the paper Atomic, Molecular and Laser Spectroscopy. After completing this module, we will be able to understand the spectra of alkali atoms, its introduction, spectrum of sodium, the quantum mechanical view and screening constant, doublet structure of sodium series lines with spin orbit interaction and spin orbit interaction energy for non-penetrating orbits, spin orbit interaction energy for penetrating orbits as well, and spectral lines in emission spectra, intensity rules, etc. The series of alkali atoms contain lithium with Z is equal to 3, sodium with Z is equal to 11, potassium Z is equal to 19, rubidium Z is equal to 37 and cesium with Z is equal to 55, and their configurations are 1s2, 2s, 1s2, 2s2, 2p6, 3s, 1s2, 2s2, 2p6, 3s2, 3p6 and 4s, and in the last we have the 5s and the 6s, and this suggests that an alkali atom consists of one or more closed shells of electron in its ground state and a single valence electron in a new shell in ns orbit. Now visualizing the two particle system with a lone electron, means valence electron, subjected to Coulomb field of point charge that is equivalent to proton of the diameter approximately 10 to 15 meter and is thus the simplest spectra. The aim is to solve this two body system exactly to find the wave functions and understand the meaning of four quantum numbers N, L, Ml and Ms. Keeping in mind the shell model to understand the structure of the alkali spectra, and it is a fact that the fine structure and magnetic field splitting are smaller than the gross structure energies by a factor of fine structure, and the field splitting of the transitions lines can be understood after the gross structure of the spectrum. So far, on the basis of the shell model, the atomic states are known as. The electronic states are specified by four quantum numbers N, L, Ml and Ms, and electrons with L is equal to 0, 1, 2, 3 are called sp, d, f electrons respectively. The gross energy of the electron is determined by N and L. In the absence of fine structure and external magnetic fields, all the states with the same values of N and L are degenerate. Each NL term of gross structure therefore contains 2 into 2L plus 1 degenerate levels. According to Bohr model, radii of the principal atomic shell of normal sodium atom with atomic number 11 are 0.05 angstrom, as 1s electron sees plus 1 nuclear charge, or valence electron of sodium is moving in a net field of plus 1 e charge due to core of finite size, apparently like a lone electron in hydrogen atom moves around the proton, which is a point charge. Therefore, it is assumed that the spectra of sodium atom are expected to be analogous to that of the hydrogen, as in both the cases respective valence electron moves in a net field of, but with the difference that the field is from the finite size core in former, whereas from a point charge field in the latter case. So this table illustrates about the values of N, L, Ml, Ms, sigma ml and sigma ms corresponding to n values 1, 2, n is equal to 2, 2 plus 6, n is equal to 3, 2 plus 6 plus 10, and sigma ml, sigma ms in all the cases have to be 0, and ml values correspondingly and ms values correspondingly are given here as. The closest shell has 0 total angular momentum and 0 spin angular momentum and designated as 1 as 0. The valence electron can be excited to various SPDF orbits. Those results in doublet terms. Quantum mechanical view of spectrum of sodium. As the potential energy in hydrogen atom is spherically symmetric, that is, it depends only on the radial coordinate r, its solution for all spherical symmetric systems may be expressed as psi r theta phi is equal to rr y lm theta phi, where y lm theta phi are spherical harmonics, and we can substitute this in the Schrodinger equation written in polar coordinates. The Schrodinger equation in polar coordinates is 1 by r square curly upon curly r square curly psi upon curly r plus 1 by r square bracket 1 by sin theta curly upon curly theta sin theta curly psi upon curly theta plus 1 by sin square theta curly square psi upon curly phi square bracket close plus 2 mi upon h cross square E minus V psi is equal to 0. This leads to the radial equation 1 upon r square gd of r square dr upon dr plus 2m upon h cross square E minus Vr minus L into L plus r upon r square r is equal to 0. And the angular equation L square y lm theta phi is equal to h cross square L into L plus 1 y lm theta phi, where L square is equal to minus h cross square 1 upon sin theta curly upon curly theta sin theta curly upon curly theta plus 1 upon sin square theta curly square upon curly phi square. Orbital angular momentum operator has eigenvalues corresponding to eigenfunction y lm theta phi. The orbital angular momentum for a completely filled shell according to Pauli's principle is 0, and therefore their charge distribution is spherically symmetric. Accordingly, in the case of sodium atom, for that matter in case of all the alkali atoms which are similar to sodium atom, charge distribution in shells, that means completely filled shells, is spherically symmetric and is known as the core of the atom. Valence electron 3s is therefore regarded as moving in a central force field. This central force field is that force depends only on distance and is completely independent of the angular position of the core. Therefore, quantum mechanically, also spectrum of sodium is expected to be similar to that of the hydrogen atom. So there are certain experimental observations. The transition of the electron from one energy level to another is governed by the selection rules, which is delta L is equal to plus minus 1. And experimental findings reveal that emission spectra of the alkali atoms can be analyzed into 4 chief series with the peculiarities as we can discuss. First series consists of doublets, and we take the separation in centimeter inverse between the doublet components remaining constant as far as the series extends. Series is termed as sharp series. This arises due to transition from 2s states to lowest 2p state. The lines are observed in visible and infrared regions and are quite narrow. The second series consists of doublets. The separation is again taken in centimeter inverse between the doublet components, decreases rapidly as the series extends to higher members. Series is termed as principal series. This arises due to transition from 2p state to 2s state. The lines are intense and are observed in absorption spectrum as most of the atoms are in the ground state. The lines of this series are in ultraviolet region except one in visible region. The third series initially consists of triplets. Triplet means 3 components followed by apparent doublets. Separation is again taken in centimeter inverse between the outer components remaining constant as far as the series extends. Series is termed as diffuse series. This arises due to transition from 2d state to 2p state. The lines lie in the visible and infrared region. The lines of this series are diffused on one end or both the end of the line. Fourth series is termed as fundamental series that lies in far infrared region and consists of very close lying doublets. This arises due to transition from 2f state to the lowest 2d state. The lines of this series are in visible and infrared regions. So one can understand the sharp, diffuse and fundamental series occur in emission spectra. The sharp and diffuse series have common limit whose wave number is equal to the lowest p term that converge to two limits corresponding to doublet components. The difference between the convergence limits of sharp or diffuse series and the principal series is equal to wave number of the first number of the latter, means principal series, and this is referred as Rydberg-Ritz's law. This forms one of the bases for analysis of atomic spectra. The difference between the limit of diffuse and fundamental series is equal to the first line of diffuse series. Each series in alkali atoms converge towards shorter wavelength similar to that of hydrogen. In absorption spectrum at moderately low temperature, only principal series is observed, implying lowest term as Ns, and the series appears similar to the Lyman series of hydrogen atom. The figure depicts the transitions forming four chief series: principal series, diffuse series, sharp series. The figure is self-explanatory, showing all the chief series. The SP, D and F series corresponding to various different values of N and L are shown in the figure. Transitions are drawn in accordance with the selection rules. That means the principal quantum number can change by any value, whereas by unity only. That means delta L is plus minus 1. The alkali spectra comprises of series of lines, that is doublets, with successive decreasing separation and the intensity as well, in a fashion similar to that of hydrogen spectrum. The transitions forming the four chief series in alkali spectra may therefore be summarized as: sharp series, the transitions are from N0P to MS. Principal series, the transitions are from N0S to MP. Diffuse series, it is from N0P to MD. And fundamental series from N0D to MS, where M assumes the running values. Principal quantum number, which is a measure of the total energy for the hydrogen atom, is shown on the right hand side of the figure. The figure depicts the sodium alkali atom, its various transitions and various states. The comparison with the hydrogen atom leads to the fact that the energy levels of sodium lie lower on the energy scale. This suggests that the kinetic energy and therefore velocity of exciting valence electron in sodium is greater than the corresponding value of the valence electron in hydrogen atom. On the other hand, velocity of valence electron decreases with increase of its principal quantum number and increases with increase of effective charge, in the field of which valence electron moves around the nucleus. The latter dependence makes it imperative that the valence electron in case of sodium atom sees more than plus 1 e charge, and this is possible only if the valence electron penetrates in the core of the atom, that is, electron orbit is elliptical. In addition, deviation of the potential from the Coulomb potential due to a point charge causes the term value to depend on, and smaller the value, larger is the eccentricity. Thus, the penetration increases with the decrease of value, and hence the electron experiences more nuclear charge during its penetration. Therefore, the electron moves part of time in a field of greater effective charge. Also, close proximity of the electron distorts the core, leading to electrostatic polarization. Both these effects increase the force of attraction and hence lower the total energy. Difference in energy is attributed to the various amounts of penetration into the core. Orbits that penetrate the core are called penetrating orbits, and those doesn't are non-penetrating orbits. While describing through quantum mechanics, these effects are taken as first and second order perturbations respectively. Following the Rydberg relation, lines of sodium can be represented by a general formula where nu is equal to r upon m1 plus mu1 square minus r upon m2 plus mu2 square. m1 is a fixed number, m2 is a running number, and mu1 and mu2 are the Rydberg constants. On comparison with Balmer formula and the quantum number n of the valence electron in sodium or of alkali atom, one finds that n is greater than the Rydberg denominator. That is, n is greater than m1 plus mu1, and n minus m1 plus mu1 is equal to delta 1, and n minus delta 1 is equal to m1 plus mu1. Similarly, one can write down n prime minus delta 2 is equal to m2 plus mu2, and substitution of m1 plus mu1 and m2 plus mu2 in the above equation gives us nu is equal to r upon n minus delta 1 square minus r upon n prime minus delta 2 square. The equation has principal quantum number n, delta, s that measure the extent of penetration, and it is inferred that larger the value, greater is the penetration. Considering the first number of the principal series, that means from 3s to 3p of sodium, the experimentally observed first number is expressed analytically by the following transition, that is nu is equal to r upon 1.637 square minus r upon 2.117 square is equal to r upon 1 plus 0.637 square minus r upon 2 plus 0.117 square, where we have just broken down the denominator terms, writing 1.637 is equal to 1 plus 0.637 and similarly 2.117 equal to 2 plus 0.117. Principal quantum number of sodium valence electron is 3, and the above equation could equally be written as nu is equal to r upon 3 minus 1.373 whole square minus r upon 3 minus 0.883 square. Thus, we found delta 1 and delta 2, delta 1 equal to 1.373 and delta 2 is equal to 0.883. These are the quantum defects in 3s and 3p levels respectively. This means that the s orbit is penetrating more than the p orbit, and similarly one can write down corresponding to sharp series nu is equal to r upon 3 minus 0.883 square minus r upon 4 minus 1.357 square, and for diffuse series nu is equal to r upon 3 minus 0.883 square minus r upon 3 minus 0.010 square, and for fundamental series nu is equal to r upon 3 minus 0.010 square minus r upon 4 minus 0.001 square. Screening constant. Lowering of term series is explained using the concept of quantum defect that itself measures the extent of penetration of the valence electron. Valence electron on penetration faces charge more than unity as it should, while the electron moves well outside the atomic core, means non-penetrating orbit. This has got the attention of using effective quantum number. We can denote it by n star, which is less than n, or the empirical adoption of the Balmer formula for the non-hydrogen like spectra can be made by using the effective nuclear charge, again denoted by Z star, in the numerator of the relation. Thus, one can write down Tn is equal to Z minus sigma square upon n square into R is equal to Z star square upon n square R. Here sigma is known as the screening constant that measures the extent to which intervening electrons screen the nuclear charge. Sigma remains almost constant within an isoelectronic series. This helps to find screening constant and n as well by plotting this under root of T by R against that are known as Moseley's graph. Now we would like to understand doublet structure of sodium series lines considering spin orbit interaction. The splitting of the levels and hence splitting of the lines is due to spin orbit interaction on the valence electron of alkali atom. All the energy levels of the valence electron of alkali atoms except L is equal to 0 are separated into two. One level corresponding to P, a total angular momentum J is equal to L plus 1 by 2 and the other J is equal to L minus 1 by 2 with the second lying power than the first. The shift or the interaction energy delta T is given by delta T is equal to minus R sigma square Z raised to power 4 divided by n cube J into J plus 1 minus L into L plus 1 minus S into S plus 1 divided by 2L into L plus 1 by 2 L plus 1 is equal to minus A J star square minus L star square minus S star square upon 2 is equal to minus lemma, where A is equal to R alpha square Z 4 divided by n cube L into L plus 1 by 2 L plus 1 and J star square means J into J plus 1 and L star square means L into L plus 1, and similarly S star square is equal to S into S plus 1. When measured from the series limit, the term value of any fine structure component is given by T is equal to T naught minus lemma, where T naught is a hypothetical term for the center of gravity of the doublet, and lemma gives the shift in units of A of the component term from T0 separation between the doublet components is given by the difference between their lemma values. For an S electron, L is equal to 0. Therefore, J is equal to S, leading to delta T is equal to 0. Therefore, all levels in series S are single. Z is in the numerator of the equation and hence increases with the increase of the atomic number. Therefore, delta T for lithium is less than delta T for sodium and is less than delta T for potassium, which is again less than for delta T rubidium, less than delta T for calcium. Delta T decreases with increasing N and delta T decreases with increasing L. These are in agreement with the experimental findings. Now coming to spin orbit interaction energy for non-penetrating orbits, the difference in the term values is attributed to polarization energy of the atomic core for the non-penetrating orbits. This deviation is understood by using the concept of quantum defect. The term value now becomes Tn is equal to Rz square upon n minus delta whole square is equal to Rz square upon n square effective. N effective means n minus delta, where Z is the effective charge and is equal to 1 for neutral 1 electron atomic system and is equal to 2 for singly ionized atoms and so forth. Rewriting the above equations in terms of screening constant, Tn is equal to Z minus sigma square upon n square into R, which is equal to Z star square upon n square R in centimeter inverse. Applying the same reasoning, spin orbit interaction energy, that means the shift for the non-penetrating orbit, is given by delta T is equal to minus R alpha square Z minus sigma raised to the power 4 divided by n cube J into J plus 1 minus L into L plus 1 minus S into S plus 1 divided by 2L into L plus 1 by 2 L plus 1, and the units are centimeter inverse, giving the separation between the doublet components as delta nu L plus 1 by 2 minus L minus 1 by 2 is equal to R alpha square Z minus sigma raised to the power 4 upon n cube L into L plus 1 centimeter inverse. Spin orbit interaction energy for penetrating orbits. An electron in the penetrating orbit spends part of its orbital time period inside the core. It means that the orbit may be considered to be consisting of two segments, one well outside the core and the second is within the core. Interaction energy is calculated, first considering that the electron is completely outside the core, where it experiences effective nuclear charge Z0, then separately as if the orbit is completely inside the core and faces altogether different nuclear charge, say Zi. Both these interaction energies are combined, taking time weighted contribution. As the time spent within the core is just a fraction of the time, say t, required to traverse the whole path of the orbit, one makes an assumption that time required to traverse segment outside the core to a first approximation is equal to t. When the electron is well outside the core, from the above relation, delta nu naught is equal to R alpha square Z naught 4 upon n naught cube L into L plus 1. And when the electron is taken to be within the core, the relation is delta nu I is equal to R alpha square Zi raised to the power 4 upon ni cube L into L plus 1. N naught and ni are the respective quantum numbers. Now, time period of the electron's motion is t is equal to n cube h cube divided by 4 pi square me 4 z square. Time required traversing when the orbit is outside and when the orbit is within the core. Resultant value taking time weight contribution is given by this relation. One obtains by approximation T0 is equal to T, and we get the final result delta nu is equal to r naught square z naught square upon n naught square L into L plus 1 z naught square plus zi square centimeter inverse. When the valence electron penetrates deep into the core, ZIE is greater than Z naught E, particularly for the heavy elements. The equation can therefore be approximated further to delta nu is equal to Na square Z naught square Zi square upon N naught square L into L plus 1 centimeter inverse. Inserting the screening constants for each of the Z's in the above equation, one arrives at delta naught, thereby replacing the terms Z naught and Zi as frequency F is linear velocity v upon 2 pi r, using the relation for nu is equal to 2 pi square e square z upon n h and r is equal to n square h square upon 4 pi square me raised to the power 4 z, and one gets f is equal to 4 pi square me raised to the power 4 z square upon n square h square, and using t is equal to 1 by f one obtains the relation. The other alkali atoms are lithium 1s2 3s, potassium 3p6 4s, rubidium 4p6 5s, and cesium 5p6 6s. Spectral lines in emission spectra. Intensity rules. Intensity of a spectral line is defined as a measure of the number of photons of exactly the identical energy arriving per second at a point that corresponds to the energy of the photons in the electromagnetic spectrum. For a change delta L not equal to 0 in the transition from one term to another in LS coupling, the strongest lines are those for which delta J has the same sign as delta L. Of these, the intensities of the lines increase as the magnitude of J increases. For a change delta L not equal to 0, the weakest lines are those for which delta J and delta L have opposite sign. The lines with delta J is equal to 0 are intermediate in intensity. Let us apply these rules to the structure transitions of first member of diffuse series. The transition is from 2d 5 by 2 to 2d 3 by 2p 3 by 2. Delta J is equal to 0 and delta L is equal to plus 1, while for 2d 3 by 2 to 2p 1 by 2 transition, delta J is equal to 1 and delta L is equal to plus 1. That is, delta J and delta L have the same sign. From this, it is clear that the transition 2d 5 by 2 to 2p 3 by 2 is stronger than 2d 3 by 2 to 2p 1 by 2, as the former involve a larger value of J, and the transition 2d 3 by 2 to 2p 3 by 2 is weakest as delta J is equal to 0, though delta L is equal to 1. So, quantitative rules for relative intensity from an initial level or to a final level of a multiplet is proportional to the statistical weight 2j plus 1 of that level. The constant of proportionality is common to all levels of a given multiplet. Conclusively, the transitions are 2d 5 by 2 to 2p 3 by 2, 2d 3 by 2 to 2p 3 by 2, and 2d 5 by 2 to 2p 1 by 2, which is a forbidden transition with 0 intensity, and 2d 3 by 2 to 2p 1 by 2, wherein 2d 5 by 2 to 3p 3 by 2 and 2d 3 by 2 to 2p 1 by 2, delta J is equal to delta L is equal to plus 1, that is, changes in J and L are in the same way, therefore intense lines arising from these transitions. One of these two, 2d 5 by 2 to 2p 3 by 2, is more intense because it involves larger J. On the other hand, third allowed transition yields a weak line because changes in J and L are not in similar manner. All these transitions are shown in the figure, and we can look to the remarks that the intensity rules may fail to explain the experimental results, particularly for the higher members of the series of the alkali spectra. The deviations have been understood to be due to the perturbations of the higher levels. So, now summarizing what we have learnt in this model is, for a given value of n, S levels lie deepest, followed by P, D and F levels, and quantum defect for a given value of n is a function of L. And for a given value of n, eccentricity of the elliptical orbit decreases with the increase of the value of L. That is, as L approaches n, the orbit is tending to be circular. For spherical lines may be written in a general form like nu is equal to r into 1 upon n double prime square minus 1 upon n prime square, where n star is equal to n minus delta 1 and n prime is equal to n prime minus delta 2, where n star are termed as the effective quantum number. It is observed that the quantum defect is constant within one term series, but is slightly larger for lowest term value. Relation between the two to first approximation may be thus written as n star is equal to n minus alpha L. And to take care of slightly higher value of quantum defect in lowest term values, n star is equal to n minus alpha L minus beta L by n square. Or this relation is known as Rydberg-Ritz formula. Alpha and beta are normally positive and are constant within a series of term values, and beta is quite less than alpha and is therefore negligible. Thank you.